that was enough time to read most of this stuff. Let me share the right screen now. All right, is everybody seeing the Kindle book?
Yes.
Thank you. Okay, so this section is pretty dense, and so we should just go through it, and but you won't, you know, it's a lot of software engineering type stuff, and some of you will probably be familiar with these kind of things, and others won't. The only way to really learn it, I think, is to be able to get involved and do some examples. You have to have, to learn something like this, you have to be forced to do something that uses it. So, but for this today, we'll just go through this material, and you'll just sort of see an overview of what it is. So the theme of this section on the TF record format is how to compress, store, and then access data in binary format in order to make it, in order to be able to handle it with the limited hardware that you have. So it's mainly for use with very large data sets. So they talk about what this thing is, and it's something. It has a checksum in it. It has a checksum to make sure that the data has been stored correctly. And I had encountered the term before, but I didn't know what CRC was. So I looked it up, and it's a cyclic redundancy check, and there's a Wikipedia page on it, which I haven't read yet, but it's mainly a way to make sure that your data is not corrupt. Okay, so they show you how to make. Let's see. I'm trying to compare my book with what I've got here. Let's see. Back up. TF record format. Okay, so here. So they show you some code that tells you how to write a record, how to write something in TF record format, and you have to use this tf.io.tf record writer class. And this is a context expression. And this tells you how to write a simple 2-record data set, and then how you can read it back. The second thing. Okay. There's a way to compress things if you wanted to compress them. I think I said compress before, but it's really just storing it in binary format here. It's not compressing them. But there's a way to compress tf.io.tf record options compression type equals gzip, for instance. That'll compress it in a gzip format. And then when you read it, you have to specify the compression type so that it knows enough to decode it. All right. Any questions up to here or comments? So far, pretty straightforward, but there's a lot of methods that you have to be aware of that are needed to be able to do this stuff. The tf.io.tf record writer and tf.io.tf record options, and the other one, tf.data.tf record data set, in order to read stuff. So there's 3 commands you have to be aware of here. And then as we go on, it just gets thicker and thicker with the number of commands we have to get familiar with. But it's just a matter of writing down these things and studying them and understanding what they do, and then you'll be able to use them when you need them. Any questions so far? Okay, so The next part is an introduction to protocol buffers. They call them proto-buffs. And apparently this was a format that was invented by Google. And so they give an example of one. And these things are called messages for some reason or other. I think they give the reason historically. In this command, syntax, this starts with syntax equals proto3. The proto3 is the version of the protobuf thing that we're using. So it's something that you can't change. I guess it's the latest version. And then you specify a message, and then you give it a class name. So message is something that is involved with this protobuf thing. It has a meaning. And person is a class that you're defining here, and you're giving it a string name, an int32 ID, and a repeated string email. So this is how you just define this thing. Okay. Okay, next page. So we've just defined a person object, and we've given it a name, we've given it an ID. Oh, sorry, I read through that a little too fast. Back to one page. Sorry. Yeah. So we're defining a name, an ID, and a let's see, I don't understand what this is yet. We'll have to come back to it. But we're basically defining the type. We're saying that name has a string type and its value is 1. ID has an int32 type and its value is 2. I guess email, so then we're also defining email to be a repeated string type and have a value of 3. In this case, they're showing us that email can be, so each person has a unique name and a unique ID, but they can have different emails, right? You could have an email address on Gmail, and you could also have one on Hotmail and whatever. You can have as many email addresses as you want. So the email type is a repeated string. And that's just for this example. All right, number 1, 2, and 3. So we're defining fields then. We're defining the name field, the ID field, and the email field. These details about protobufs are just to give us an overview of it, because TensorFlow takes care of protobufs, as we'll see in the next session, but we should just go through this for now. He says here, all you need to know is how to use protobuf access classes in Python, and but now he's just going to illustrate the basics. So person underscore PB2 must be some package that's accessible in Python, and then person is the, let's see, person PB2 import person. I thought we generated this class just previously. So now we have access to this class, and we can instantiate a person with a name Al, with an ID, and with an email. So this is an instantiation of the person class. And then we can display the class, and we can read off, this is just ordinary Python objects. We can read off the field, we can read off the name field, we can modify the name field, we can read off the first email address, and we can add a second email address if we want. And then this part is interesting. This is this method called serialize to string. This is where you take the object and create a binary file, create a binary object out of it. So s equals person.serialize to string serializes the object to a byte string, which is a binary kind of object. Well, no, it's not a binary object yet. It's a byte string, and then if you show it, if you then print s, it shows this b, which says that it's I guess B denotes byte string, and then what's inside the string is all the pieces of our definition: the email address, the ID, and the name, and so on. So then this is how you create a new person. This creates an empty person. Then we fill it with this parse from string command of S. So basically, you're just creating person 2 and copying into it all the details that you just created in this person object. And then you can test with this command. You test and see that they're equal. Okay, so he's shown how to create a class, play with it, look at it, look inside it, change some of its fields, and serialize it. And then, so serialize to string, I guess, is how you encode it to a binary object, and then parse from string is how you read the binary object back into ordinary format. But now he says, let's see, we could have serialized the person object to a TF record file, and then we can load and parse it. But serialize to string and parse from string, those are the two commands that we used to encode and decode the string, are not TensorFlow objects, and so they can't be included in a TensorFlow function. And so now we go to the TensorFlow methods for dealing with protobufs. So this is sort of a complex and dense kind of material to get through here. But the main idea to get out of it is that you're creating a class and you're giving it some method, some objects in the class, and you're encoding it in binary format, and then you're saving it, and then you're decoding it back to ordinary format, back to text format. So that's sort of the overview. Any questions up to here or comments? Okay. Does anyone have experience in this area? Has anyone done operations with TensorFlow protobufs? Yes, no? I guess not. Okay, then let's go on to the TensorFlow way to deal with these things. Remember, sort of to keep in your head that what we're doing is we're learning how to save our data in a efficient format, in an efficient binary format. So the ultimate goal is to be able to read from, from read input training data from, let's say, from comma separated, CSV files, put it into a binary format and save it, and then later on retrieve it. So that's sort of the overview of to keep in mind what we're doing here. Okay, so now he defines this TF, the main protobuf in a TF record file is this example protobuf. And here's what it has in it. It has this thing called, it has a bytes list, a float list. Bytes list is meant to store binary values. Float, I guess, strings too. Float list is meant to store, floating points, and int64 list is meant to store integers. And then this object called feature is either a bytes list, a float list, or an int64 list. So I hadn't seen this before. This is a Python construction, one of kind, and then it gives a dictionary of these kinds, a byte list. Let's see. So this is the type bytes list, and this is the actual object bytes list equals 1. This is the type float list, and the float list is initialized to be 2, and this is the int64 lists, and it's initialized to be 3. Okay, so then there's this other construction called features, which somehow maps a string into a feature. And this part here, I think this is some ID. The feature equals 1 is some ID. That's all I can understand about it, because from the way he defines it later on. Okay, so this is the
So I
yeah,
had a query.
yeah.
This is an example of the sequence example. Sorry, this is a sequence example protobuf, which is already there in the TensorFlow API, right?
I believe so. So we're becoming familiar with the format of it.
Hmm.
So there's all of these sort of Russian dolls to these Russian doll things to get into our heads. There's this bytes list. So the smallest components are the byte list, float list, and int64 list. Then there's a feature that's made up of so then you can have these capital F feature things that are made up of either one or the other of these three types. And then there's a features object, which is made up of uh, some kind of let's see, maybe it'll be more clear, a map of a feature and an ID. So
Hmm.
you map a string into a feature object, and then you give it an ID.
Hmm.
And then, so that's another level. And then the final level is example, uh, which is a which is a features object with its ID.
Hmm.
So that's how I understand it. Oops. Then he talks about packed equals true is used for repeated numerical fields for more efficient encoding. Um, I don't see an example of where he's using that. Um, features with an S contains a dictionary that maps a feature name to a corresponding feature value. So features with an S, we have to distinguish between this object feature and this object features. So features with an S contains a dictionary that maps a feature name to the corresponding feature value. So let's go and look at this. Features. So the feature name is the string, and then uh, the feature, the capital F feature is one of these bytes list, floats list, or int64 list objects is the value. And then, as far as I can tell, this feature equals one thing gives it an ID. So that's one thing. And then the next level is the example, which is a dictionary that contains one of these objects and its ID. So features equals one is its ID. And then okay, so that's enough for now. Any questions up to here, or uh, comments, or trying to figure out what's going on here? I mean,
So it looks like the message is kind of nested, kind of a JSON type of object.
this part here, it looks like a JSON kind of object.
It's nested, at least, looks like.
Oh, nested, yeah. So yeah, that's true. So you have a feature. So message is a feature, or this message. Okay, sorry. Feature is a message object. That's what we're looking at here. So this message is telling you what kind of object you have here. Um, so int64 list is a message, and we've defined messages on the previous page. Oh, and here's the packed equals true format. So so you can compress the storage, I guess. That's what it says here. Packed equals true is used for repeated fields for more efficient encoding. So if you have a list of objects, which this is, a float list, which is a repeated float, and they initialize it to 1, but you can put more stuff in it. The bytes list is not given this packed equals true format, so it's not, I guess it's just one thing. It's not being repeated. Oh no, it says it is repeated. So I'm not sure why they don't say packed equals true for it. Oh, because it's numerical fields. It's numerical fields, and bytes list is not a numerical field. Okay, so that's that mystery. So they're defining a sequence of these message objects, and let's go back for a moment and look at what a message object is, because we just saw it. And here it is. It's a class that has a name, an ID, and an email. So the name is of type string, the ID is of type int32, and the email is a repeated string. So this is what the idea of what this message feature is. Sorry, I shouldn't use that word feature. This message object is. Okay, so now we're building things with message objects. So there's this hierarchy. So we have this bytes list that is a message object. I should mention that I think, well, let me just go on then. So this is a message object, this is a message object, and this is a message object. There's three kinds of, and these are sort of the elementary building blocks. Then we build features, these capital F features, is also a message object that's built from one of these three elementary, sort of more elementary objects, okay? And then the next in the hierarchy is features, the features object. It maps a name to a feature object and gives it an ID. And the name is a string, okay? So all that is pretty abstract. So next he gives an example, okay? So here's how you this is creating a tf.train example. So now we're getting back to reality, back to the reality that we know of a training data set. So here's how you write the train, this example representing an example representing the person that we had earlier, and write it to a TF record file. So here's how it works. From TensorFlow.train, import bytes list, float list, int64 list. So TensorFlow knows what these things are. From TensorFlow train, import features, and example. So it knows what these things are. So as Mayank was telling us, this is internal to Tensor. This is represented internally in TensorFlow. It knows this. It knows these definitions in this hierarchy. So now all we're doing is importing those things. Now, once we have all of those classes and so on that are available to us, we can actually create one. And so now we're going to do this person example equals, we're going to create a class, we're going to create an object of class example with features equals objects from the class features with, and the feature is a name, which is a feature of type bytes list, an ID, which is a feature of type int64 list, and with emails, which is a feature of type bytes list. And so this is a sort of the Byzantine code that you have to go through to create one of these objects. And once you've created it, okay, now that we have an example protobuf, so we've just created an object called an example protobuf, and the next thing you have to do is to write it into a TF record file, like we saw before. These are the binary files that TensorFlow uses to store, input data that could be text or could be images or stuff from your training set, and it stores it in a compact and fast and efficient format, and that's the whole point of all this. So once we've created this protobuf, then we can write it into a TF record file. And to do that, we've created this person example. We have to serialize it to string. I guess that operation has to be done before we write it into a record. So this is just a simple example that he creates to just show us the minimal, what it looks like at the minimum. But he says typically you have to create a script that reads from your current format, which we're familiar with CSV files. So you're going to read each example, create an example protobuf for each instance, serialize it, and save it to record files, and shuffling them in the process. So this is how you would have to deal with data that is gigantic, too big for your machine or hardware to handle. Okay. So he says that he says this requires a bit of work. So once again, make sure it's really necessary. Perhaps your pipeline works fine with CSV files, and I'm hoping that most problems that I encounter that will be true. But anyway, so moving on, he stored the TF record file containing serialized example. The next thing you have to do is to load it and parse it. Load it and then parse it. That is to convert it to ordinary format that you can deal with. So to load the serialized example protobufs, you use tf.data.tfRecordDataset, and he does it down here. Let's see. TF feature. Trying to see where. Parse each example using tf.io.parse single example. So this is something that comes with TensorFlow. It's a method that comes with TensorFlow. It requires a string scalar tensor containing the serialized data and a description. And the description, a description of each feature. The description is a dictionary that maps features to either a tf.io.fixed. I feel like I'm just reading this. I'm not really, since I haven't used it before. The following code defines a description dictionary. So let's see what this next line is doing here. Defines a description dictionary, then iterates over the TF record data set, parses the serialized example protobuf. So feature description, name, value, ID, emails. So this is one of those message things that we've seen. So this is telling us what the record that we're going to read looks like, and it's specifying its form. That the first part of it is a name that's a string, the second part is an ID that's an int64, and the third part is a list of emails. That's why it's called a var-len feature. That means it can have, you can add to it. It can have more than one thing in it. Okay, so we've saved this thing called mycontacts.tf record. So now we're going to try to retrieve it. For serialized example in tfdata.tf record dataset, parsed example. So this is how we're getting into this file that we saved called mycontacts.tf record. We're reading each example, and then we're parsing the example. And we're giving it this feature description to tell it what the things that we're reading, what the records that we're reading are look like. Fixed length features are parsed as regular tensors, but variable length features are parsed as sparse tensors. Remember, we have one variable length feature that is the emails, and that can be that can have more than one object in it. you can convert a sparse tensor to a dense tensor by using this TensorFlow sparse to dense function. But he says in this case, you can just access the values. So what's he doing here? Parsed example. Okay, so we've read this parsed example, right? We've accessed our stored record, and we've read I guess in this case there's only one record in it. So we've read this example into this object called parsed example. So now we can access what's in parsed example. It's a dictionary, and we can grab out the emails, part of it by giving it the key of emails, and then and get the values out. So in this case, we had a list of two emails, a@b.com and c@d.com. If you remember when we created this thing, and so when we print these values out, that's what we get. It's a NumPy array, and it has these two objects in it. Okay. Now he's reviewing what this bytes list object is. I think we saw this before. Let me back up a page. This bytes list is coming from here, and it's a way of storing binary data. And he says you can even, because the serialized object is binary data, you can store that. So so I guess if you had a training data set that had images, then you might encode, you could use this this encode JPEG feature to convert the image into a binary object and put it in a bytes list. And then when you read the record, it parses the example, and then it has to call decode JPEG to get back the data in the original format. And then he says there's another way. If it is another way, instead of tf.io.decode JPEG, you can use tf.io.decode _image, which knows how to decode a variety of image formats. Tells you how to store tensors in a bytes list by serializing the tensor. So serialize, this idea of serialize, I think it just means convert it into binary format. Can anyone expand on that? I mean, also serialize can, so there's these three terms that are floating around: serializing, binary format, and byte string, and I think they're all the same thing. Can anyone expand
Yep.
on that?
Yep, I think so too. Serialized to the byte string, because we are storing this byte string in the TF record. If I've not yet tried to open it, because there are TF records in the folder that you're trying to save to. And if I try to open it, just go to that file and try to open it. Maybe it's some sort of, okay, it's encoded. So it's the binary, the stuff that we get when we compile something, I suppose.
Yeah.
Yeah.
So the idea then is this: when you see serializing, when you see byte string, it means these objects are in binary format. And
Yeah.
this bytes list then is a way to store things in binary format. So that means images, or it could be, if you're doing NLP processing, natural language processing, then you would have text that you could convert to binary format to make it easier to store or quicker to store. And so it's giving methods to encode this data in binary format, and then it's giving you methods to get it back, which they call parsing it. So you start with some data that's been encoded in binary format and you want to get it back out in ordinary format, then you use this this method. If you know if you already know that it's a tensor, that you've encoded a tensor in binary format, you can undo it using this. If you know that you've encoded something in a JPEG image, then you can get it back using decode JPEG.
Decode, yeah.
Yeah, decode underscore JPEG. If you know it's in a PNG format, you can use decode underscore image method to get it. So these are the methods in TensorFlow that you can use, that are used to both encode and decode things into binary format. So encode things into binary format and decode back to, back to ordinary format.
Is it binary or is it byte format?
I think it's the same. I think those
think-
things mean the same thing.
I think it's byte, like it's writing out like a text. Binary would be just zeros and ones, right?
Okay. So
when you're serializing, like I think in PyTorch or all that stuff, you basically just write down, like if it's like the final model that you're saving, then it's like a dictionary that gets written out, which is just string values or byte values in that sense.
Yeah, it's byte fields, I think.
But why would you convert images into
like
bytes?
Basically, instead of writing 255 as a number, I think it's just 255 as a string there.
Yeah, I suppose.
I
Okay,
don't see
so
the advantage. Yeah, I'm also not very clear on how you save on memory or space, one versus the other. I'm not clear on that.
Okay, so I think you're right then, because I remember seeing on the previous page when you could actually print out one of these byte strings, and it doesn't print gobbledygook, it actually prints characters. So I guess I should back up and say that serializing then means converting things to byte strings, which are just series of alphanumeric characters. Is that what your understanding is, Rekil?
I think if you're writing it out as an integer, then you have to allocate that much space, right? Irrespective of whether it's going to take it up or not. Whereas if it's byte formatting, then you have that flexibility of variable length. I just quickly pull that up on Google. I think that is my understanding.
Okay, so that makes sense.
But that's where it saves, yeah.
Yeah, so that's what this bytes list is. Then it's a list. It is a serial list of characters that has no limited space. Is that what you're saying?
Yeah, right, exactly. Like you don't have to pre-allocate that much space.
Right. So going back to these three types that we're dealing with here, we have this bytes list format, which we just discussed. That's where you convert objects into lists of alphanumeric characters. And then there's this float list object. And here it has to be floating point numbers, and an int64 list has to be int64 numbers, int64 format. So there's these three types that we're dealing with in these records. Okay, so any comments or questions here? I don't have the advantage of being somebody who's very conversant with all this stuff, so I'm just trying to present it to you as I've learned it, and yeah, so.
Yeah, so from an infrastructure point, that's why it's interesting to me that because protobuf is basically the RPC, the framework sit on top of RPC for better performance. So my question actually is, I'm looking for is, and there's also the saying about whether TensorFlow versus PyTorch, which is more scalable, right? So my understanding at this point is TensorFlow is, it's developed by Google based on, you leverage the protobuf very well, the RPC protocol, whereas PyTorch doesn't. But on the other hand, I see that the MLOps, the kubeflow frameworks does support PyTorch, so which means that it can leverage this protobuf to make PyTorch as performant. So I don't know, maybe like eventually whether TensorFlow versus PyTorch, which is more perform better, I guess that's what I'm trying to look into.
So that's interesting. So you're saying that the PyTorch doesn't have an equivalent format for storing records?
Well, it might have its own, because it's just because you need to basically serialize it to make it a buffer, right? It's because you basically buffer it before you send to another computer. This is for distributed computing.
Mm-hmm.
So Google use protocol buff. Other companies use different RPC, different buffer mechanism, right, for RPC calls. So
Victor? What's RPC?
Remote procedure call. Yeah, it's a
remote procedure call. Okay.
So yeah, so protobuf is very important when it comes to Google, because Google basically all use this as the serialization mechanism, and this is also the most important serialization mechanism used in like Kubernetes, for example.
Mm-hmm.
So yeah, but so PyTorch by default doesn't use protobuf simply because it's not part of Google. But it can be serialized obviously when it runs on kubeflow on Kubernetes basically. So yeah, so eventually which framework, TensorFlow versus PyTorch, which is more perform better, that's still the question I don't have the answer yet.
Okay, thanks for that. You know a lot more about this than we do, I think, or at least than I do. I wanted to ask Srinivas, because you're familiar with a FastAI version 2 library. Do they have a way of this kind of serializing? Is there a way to store large amounts of data that can fit in memory in this efficient way?
My off the top of my head answer would be they probably rely just on PyTorch capabilities, nothing that FastAI is built unique to itself that allows this capability. And at least as far as serialization and the protobuf and those kinds of things, they are closer, or in fact even one could argue a level below like TensorFlow or PyTorch, meaning, as Victor just said, it's additional capabilities that you do in order. And I agree, or I also have the inclination, I don't know this for sure, but I'll look into it, is these kinds of capabilities exist both to allow the scaling of TensorFlow jobs and stuff to be able to successfully shared across machines and combined without loss of with efficiency and without loss of parallelism, which requires part of the serialization capabilities and stuff. That's why the RPC protocol and protobuf and all that comes into play when you start doing portions of jobs
Yeah.
in different machines and stuff. But those are lower level capabilities, which typically a library like FastAI wouldn't necessarily want to play with. It would rely on PyTorch's native capabilities for that.
I see. Yeah, I mean, ultimately, even though we have to learn how to use this now if we want to make use of these capabilities, but my feeling is that ultimately they're going to make this transparent to the user, so you won't have to know all of this low-level stuff. It's like programming, in versus programming in machine language versus programming in a normal language like Python or C++ or whatever. You don't look at like when you add two numbers together, you don't have to look at the registers and the buffers and all that stuff. I'm thinking that in the future it's going to be like this for for parallelizing jobs, partial jobs, as Srinivas says, because that's what this is all about. It's when you have a job that you can't that you have to break up into smaller units because because the whole thing doesn't fit in your RAM or on your GPU. So you have to break it up into smaller pieces and submit them one at a time or in parallel. But right now things are this awkward. We have to resort to building these objects like this, and it's just, I think it's not that hard. It just takes a little bit of experience and try. You have to, like anything, to learn it, you have to actually do a little project with it, like a homework assignment or something like that. So, yeah, that's all I can say. Yeah.
Joseph, Srinivas, Victor, and other. I have a different view. Maybe I'm just I haven't, because I haven't worked with TF records. So like at work, I have this project where I have 100,000 images. I need to train with 100,000 images, and there are like of size 256 by 256. Right. So the training set doesn't fit in memory for sure. Right. So the person before me, they tried to split it into NumPy file. But what I found recently, maybe like 2-3 months ago, is I just use like the data generators, right, from TensorFlow. So basically, what I do is, anyway, I'm training on a batch, right, a batch of 32 or 64.
Hmm.
So whenever I want that batch, my data generator just gets that batch from like a batch of 64 images, right? And I actually have the experiment running now. So to go through 100,000 images with this data generator approach, it takes about 180 seconds on a single GPU, right? Yeah, it's about three minutes to go through 100,000 images. Um, I did notice that if it's not on an SSD, it's a little bit slower. Um, but maybe okay, so maybe this is for, so this TF records and stuff is when you have like a million images to train with. Like I'm thinking, when do you go to TF records, or you're um,
Yeah, no,
Yeah.
that Mehul, I agree with you. In fact, one of the frustrations of this book when I went through it the first time in this STEM also is I wish he approached it the way FastAI does, which is show you the use case and then explain the thing behind. Because what we're struggling with is where do we use it and what is its purpose. And if that's put front and center and then you get into the detail, then it makes it a lot easier to be
mhm,
motivated to follow through and also put it in context. This is bottoms up, and at least for me, after FastAI, I'm beginning to lean towards a top down. Like, first, give me why I would use it and in what
Yeah.
circumstances,
right,
Yeah,
then explain
exactly.
all these details, because then my motivation is high to say, oh, I use it in this way. Here, we are all struggling of why would we do this and what are the conditions under which you do this, and then all these methods, as Joseph has been trying to explain, just go right past you, and you have to learn the
Yeah.
context and then
Yep.
come back, and then it'll make much more sense.
Yeah,
right,
and what would be really useful is that if he gives an example. Here
Yep.
is a job which is done by the ordinary method, by loading your CSV files, normally, and here's how long it takes, and here's how you can accelerate that, with this,
right,
structure with the serialization process. Or here's a job that you couldn't possibly do with an ordinary laptop, but with this serialization process, we can do it because we broke it up into smaller chunks. I think that's exactly right. We should have some context to understand why we're doing this and what advantages it gives us.
Yeah, there was one last thing. I shared a link. There's one Kaggle Grandmaster. So he recently, for one of the, I think it was the skin cancer challenges. Yeah, this one. Yeah. So he created these incredible like TF records of different sizes, because these images are terrible. They are like, the original images are 1024 by 3, and
Mhm.
uh, he has the TF records and the associated notebook which uses these TF records. So that this was like a really good example to just see TF records, but um, and he had some version like he went one step further, like, okay, how you can use that TF records with TPUs and with GPUs.
Wow. Uh-huh.
Yeah, uh, but I still was struggling. Like, okay, is this like I haven't seen like a comparison with okay, is it really much faster than just using a data generator, which would like maybe I don't know what's your typical training set at work, right? Like it's going to be hard to get like a million images at work, like, or 2 million.
Mhm.
Yeah, my,
Uh,
my understanding is that it only applies when you have, like, of course, number one, you need to have maybe like multiple GPU, or you
uh-huh.
want to make GPU always be like the batch. Like, I think the same chapter, I think there was one about prefetching, right? So if you don't prefetch, the GPU will be sitting idle, like doing nothing.
Yeah.
So
Right. Yeah.
if you have a multiple GPU, then you need to constantly trying to feed the data so that they will kept busy. So and also you have multiple computer even like in a network. So the product buff is helpful in this case, so they can interleave the data and then serialize them and send to the different GPU. Only then you have like you can make it. So in your case, if you only have, I don't know how many GPU you have. If you only use one GPU, then and it's constantly always busy, then this won't help.
Yeah, I see. Yeah, I was
Yep.
just looking at my, I have one GPU and my utilization is around 70%. Yeah, so it is still wasting time on, like just preparing the data and getting the data generator, getting a batch. So yeah, like you were saying, you want to see, my GPU is idle for 30% of the time because it doesn't have data, right? Yeah, maybe I can try and play with this and see if
Yeah,
it
this is
helps.
only if you have Kubernetes, like you scale out to a large cluster, right? So
I see. I see.
yeah, that's when it helps.
Well, but on the I'll share a notebook on Kaggle. Like all of us had only one TPU and one GPU, and we were still using this TF records. Let me share the notebook. Where did it
Let me
go?
stop sharing so you can share it.
Oh, okay.
Yep. Maybe try playing with the batch size. So that will have much more TF records in the memory, and then you can, I think so, utilize your GPU more.
I see. Okay. Yeah. This is my. Do you see my screen?
Yes.
Yes.
Okay. Yeah. That. Let me see. What is it? Yeah. Right now, this is without. Okay. It's worse than I thought. Yeah. This is without. This is using the data generator. So you are seeing it's using 30%, but I don't know if it's, where is it? Why is it so slow? I don't know. Okay, maybe at the end. So you can see it is. Hmm, okay, maybe when the next epoch starts, you'll see this go up. Um, yeah, now there it's starting to pick up. Yeah, I think that's the max I can get it to. And this is looping through about 100,000 images. Yeah. Um, okay, and yeah, so maybe. Yeah, I haven't. I just have my BMPs in a folder on a SSD, and yeah, that's how it's.
70 is not bad.
It's not
So
bad. Okay.
yeah, you have two GPUs here, and you are only utilizing one.
Yeah. I haven't found a good way to use. Yeah. I sometimes I'll just run two experiments on it, but yeah, I haven't found a good way to run TensorFlow with on both. Uh, okay, but
There's a distributed package which you can easily by which you can easily distribute uh,
okay,
this and this will TF records will come in handy here because
I
they
see.
are compressed and with each batch size each variable batch size you may have to those data transfers from your SSDs to this. Those buses will bottleneck it, but since it is in compressible format, which is easily decodable, so this will specifically come in handy here.
Okay, okay, I'll try it out and let you guys know. And this is the notebook where used like TF records as the input using the uh, uh, this is how the TF records were made by this person, Chris Dioetti, and and then this is just a notebook where uh, you could use those TF records. So if you want to play with it, it's a really nice notebook to try it out. Uh, I think the images are huge. I want to say it's like 100 GB total, the training set. But
Hmm.
yeah, he did something like this, like and this was it was his initial notebook, and basically we just made he made like a starter notebook, like kind of to teach you how to use TF records. And then we just made modifications on his notebook, like try different efficient nets, try different things. But for our purpose, for the TF records, um, where was the TF records used? Blah, blah, blah. Yeah, it was.
I think there's a link to that in this notebook. It's not the TF record creation is.
Yeah, it's separate, right? You're right.
Right.
And I see this thing. I don't know if anyone's like you don't make one TF record, but you split it into different TF records. Does that? I don't think he talked about that this in the notebook, in the book chapter.
Yeah.
Yeah.
Yeah, this is done to save memory, because if you have suppose image data, then TF record of 10 gigs won't be easily easy to transfer it across the bus to the GPU. So
I
yeah.
think that each training example gets encoded as a TF, gets saved as a TF record. It seems like that from reading what he said, that's what I think. Because
Oh,
in the next section he talks about this sequence example protobuf where you can make batches by randomly picking up by randomly picking out these serialized um, examples. You can make batches from them.
oh, I see. Maybe I know, like about 2 years ago, they would talk about instead of one image for one TF record, they talked about a shard of data. So, for
Mhm.
example, you would have uh, 10 shards. So each shard containing 10% of the images, and
Mhm.
um, I
So even in this case, it's a part of an image. Each record is a part of an image, and then you put it together somehow.
Yeah, I think, yeah, like it's like this. If you see train 0001 of 9, so
Hmm.
you have these 9 shards, or 9, and
Hmm.
um sorry, this is an sorry, I'm mixing two. This is a little bit older one where he actually took these images and just split it into 10 shards. But this is from 2 years ago, so
A
maybe
DICOM images is some kind of medical format, some kind of
yeah.
medical format for an X-ray or something like that.
Right,
Correct.
right, yeah. It's the most common medical format. Everybody, so even on Kaggle, when they give the images, it's normally DICOM, and somebody will convert it to JPEG or something. And
What's the difference between the DICOM and RGB or whatever?
uh,
DICOM is high def, very high definition.
Okay.
That's appropriate for medical images.
Mhm.
and
In fact, if you can access your medical records and your X-rays, and if you get raw access to them, you'll be downloading. You'll see like DICOM images for all your X-rays on your
So
medical.
is one record equal to one DICOM image stored in one DICOM image?
no, mostly one record might be like more like a set of DICOM images, because but I can try and find that. So here he has like a bunch of like here he has 0, 1, 2, 3, 4, like 14 TF records,
Mhm.
and maybe for another, I can look at the notebook, like how he created these TF records, and how many he put in there. But I think that also seems to be a user choice. Like maybe what Mayank was saying, if I was wondering like why he split it into 15 TF records, but yeah, if you put it into one, it would just take too much time to load the TF record.
Mhm. Hmm.
But yeah,
and
this.
plus, yeah.
Sorry, go ahead.
Yeah, plus in the last section that we read, at the pre-processing, like in the CSV files, they had 10 files, and uh, uh, for each batch, they were taking in 3 or 4 and then shuffling. So I think so, and that also depends upon firstly the transfer of these records from your SSD to RAM, and then from the RAM to your GPU memory
I
after
see.
each shuffle. So it also depends upon the amount of RAM that you have.
I see.
Yeah.
And also, the protocol buff is a RPC buffer. So I think the hard limit for the protocol buff is 2 gig.
Oh, I see. That seems pretty small, Victor. Like,
Yeah, actually, that's quite normal because for database operations, like for example, I work on database mostly, so the typical buffer for RPC, not UDP buffer we use, is like just like from default. Once now I'm talking about, I forgot. It's like megabyte to gigabyte. That's quite.
So then, Victor, so then if you have like an image data set that let's say it's 40 GB, right? You could put, let's see, would you encode each image in one TF record, or would you?
No, that's serialization, right? So the idea is it's going to be continuously serialized. It's just like any application communication. So it will put data into this maximum buffers, right? Let's say it's 2 gig, and let's say if the image file is huge, let's say it's 1 terabyte. In the database, have image it won't. But let's say if it's 1 terabyte, it will put into 2 gig each time, and generate in this case 14 buffer. And it will be sent to maybe 14 different computers or pod in Kubernetes. And then so they will be processed continuously. So it will then, once it's sent, it will do the next batch of 14 buffers and send again.
So these protobufs are. So I guess the question I'm trying to understand is a protobuf meant to be for one record, for one, like so let's say you have a training set with 20,000 examples or something. Is one protobuf correspond to one example? Is that how it would work?
Yeah, you can think of it like a envelope, right? So you're communicating between two computers, and you send them by each envelope contains one buffer, right? So maximum is 2 gig. So you fill them up, fill the envelope, send them again, fill another next batch of envelopes, send them again.
Is the envelope a protobuf then? What you're talking about in your metaphor?
Yeah, it's a buffer. So buffer is just like just to say it's a buffering of data into a container before or envelope before sending it.
Okay, so is the idea then that you would encode a whole bunch of images until that gets up to 2 gigs and then put that in your protobuf?
Depend on the size of data, and I think it won't be that. There's a lot of factors, I think. So if the data is huge, then you will fill up like in this case 14 protobuf and send them, and then the remaining data will fill the next 14 protobuf.
Yep.
So
Just to add, yeah. All the Google data centers use protobuf by default. So the lowest level API they have for their search engines as well as for major of their, I think so, servers that they use on their data centers. They have a protobuf as their base protocol of transport, if I'm not wrong, because I've read it somewhere. Yeah.
okay, so I guess there must be a sweet spot then, Victor. So there must be a sweet spot if you have too small. If your protobuf is too small, then maybe it takes a lot of overhead to encode and decode it, and so that would be wasteful. But then it can't go anywhere beyond 2 gigs. Is that?
Yeah, usually there are multiple mechanisms to send it, determine when to say I'm done, I'm going to send it, right? So if data is huge, usually the bigger the better, with a maximum size of 2 gig in this case for protobuf. But if data is huge, let's say image is only like 1 meg, right? Obviously, separate into multiple protobuf is waste of space, and also you don't want to wait for the many images to fill. So usually there are other mechanisms to say like I'm done, let's commit. So it will just send it before it reach the actual big size.
Because when I read through the text here, I get the impression, although I can't be sure, I get the impression that each record, each training, each example in the training set is being stored in one protobuf. Is that?
No, Joseph, I don't think about, like, for example, in this data set, like he chose to split his data into 15 TF records. So these are the 15 TF records I'm showing.
Yep.
And each is about, like, I was just seeing the size based on what Victor was saying. So like this TF record is 264 MB. And I don't know how, like, this is like a decision he made. Like, I'll divide my data into 15 TF records. And
okay.
Yeah.
I just posted something on Slack from their
Cool. Okay.
From the TensorFlow document page. I mean, it's not, sorry, not on Slack, on the chat.
Yeah, I was going to ask you if you wanted to go through that, Raquel.
Yeah, I'll stop sharing. Yeah.
Nothing. I mean, I just literally copied that. So it says in general, you should shard your data across multiple files so that you can parallelize I/O within a single host or across multiple hosts. The rule of thumb is to have at least 10 times as many files as there will be hosts reading data. At the same time, each file should be large enough, at least 10 plus MB and ideally 100 MB plus. So that you benefit from IO prefetching. That's what Victor was mentioning. For example, say you have X GBs of data and you plan to train up to N hosts. Ideally, you should shard the data in the range of 10 into N files, as long as X by 10N, that is, each file is basically 10 MB plus and ideally 100 MB plus. If it's less than that, you might need to create fewer shards to trade off parallelism benefits and IO prefetching benefits. So that's, again, I think, like what Mayank was mentioning, that you have these buses, so you want to populate them as much as you can, but at the same time, there's a trade-off between the parallelism limits.
Yeah.
That's really helpful. Yeah. So this person must have figured.
The fundamental thing underlying this is to realize that CPU accesses to memory, and that's where I think Jeff Dean, if I can find the link, I'll post it. But yes, this order of magnitude things for a cache access, for a memory access, for a disk access, for a level 1, level 2, level 3 cache, blah, 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 blah. So the point is that your IO accesses are incredibly slow. So you want them, that's part of the reason driving a lot of what this is being done. And then you want to also at the same time, once initiated, you want a large chunk to be transferred, because you can transfer at the maximum rate. If you split it too small, then you run into the problem of not getting to the maximum rate. So those kinds of considerations of the hardware that you're actually using is what drives these ratios of sizes and of what's described in the why should files be about at least 10 meg or 100 meg, or why should the gigabyte to this thing matter, and what he means by trading off parallelism versus IO prefetching. And IO prefetching is exactly the same concept as what prefetching diagram we saw last, I think on Wednesday, which says you want to prefetch on IO so that your data streaming from the memory to either the GPU or the CPU is maximum, and thereby hide the latency that you would have to accessing the data which is actually sitting on IO.
So this is all, I mean, the 10 to 100 megabytes guideline is all hardware dependent, and it could change or evolve as things get better, right?
Yeah, but these rules of thumbs cover a range. So in general, I think they are flexible enough that unless something very substantially changes, they are good for multiple years.
Yeah. Okay, well, this has all been very useful, and thanks everyone for your contributions, because I don't really know this stuff, and all of these people jumping in and helping with their viewpoints is really helpful. I did bite off more than we can chew today. We won't cover we'll start with pre-processing input features next time. So yeah, we've basically covered almost, and I didn't talk about the very last section where he talks about sequence example protobuf. Well, that's where he defines this sort of a thing that's even more more meta than the example protobuf, and it allows you to build batches and so on. So we won't be able to cover that today, but maybe we can start with that part next time when we before we jump into the pre-processing the input features section.
Sounds good.
So thanks everyone. I
Are we
really
having a
appreciate
homework
your
session
help.
later today?
I don't know if Wenchang is available for that, so I don't know. I don't know. But usually it's 2 o'clock, right?
Yep.
Okay. Okay, everyone, enjoy the rest of your Sunday.
Thanks, Joseph.
Yep.